So the way that we've defined it is not necessarily the way that it's defined in the literature, so let's see how Gaussian processes are often presented. We'll have this function of x. So f is some function. It's a random function of our data point x. It's a function that takes in an x in Rd, or Rd plus 1 if we have a dimension of 1s, and maps it to a value in R. So f is a function that takes in a vector in Rd and maps it to R. We define the kernel function k between any 2 points, x and x prime. So we don't actually construct the kernel necessarily, at least in the definition. We simply define the kernel function between 2 arbitrary points, and it can be any points that we pick in Rd. Then the function f of x, it's a continuous valued function because x is a continuous valued input. Again, we aren't restricting ourselves to the data in our definition. We're allowing this to be a function of any point in Rd. Is a Gaussian process. And y of x, this kind of shadow function, y of x is a noise added process associated with the Gaussian process. If we have this, if for any n points that we choose in Rd, so we pick n points where n is an arbitrary but finite number, and then we pick the locations of those n points arbitrarily. We construct the an n by n kernel matrix K, where the ijth entry is the kernel between point xi and xj. Then we have that the function f evaluated at those endpoints. So this is an n-dimensional vector f, where we evaluate the ith dimension of this vector. Is the function f of xi. That function is a n-dimensional Gaussian with mean 0. Sometimes you'll see this mean also be a function. We're just going to say mean is 0, and covariance equal to the kernel. And then the noise added process, given the function f, is simply a process where we take the function and add IID noise to each of the dimensions. So notice that actually these two things are equivalent, that if I integrate out f, I can actually generate y in this way, where I take my original covariance and I add the two covariances together. So the reason that we separate f is because f is the definition of a Gaussian process. So a Gaussian process we aren't going to assume has noise. We're assuming there's some underlying Gaussian process, and then the data that we observe is a noisy subsampling of this infinite dimensional function at endpoints. So in principle, this is a function over all of Rd. It's an infinite dimensional function. This is an infinite dimensional thing. But we evaluate it only at n data points. And then we observe y, which is the corruption of those n Gaussian process evaluations with some white noise. So the important thing is that the fact that we've defined the kernel and that we've defined this to be on n arbitrary points where n can be as large as we want is what makes this not just trivially a multivariate Gaussian. It's more than just a multivariate Gaussian. So let's look at an example of how I could generate a Gaussian process. So what I have here is I assume that my original data, x, is a real valued number between 0 and 1. So I'll just tell you how I generated this. I then took this and I partitioned it into 1,000 points. So I picked 1,000 points from this between 0 and 1 that are equally spaced. So the first point was 1 over 1,000, and the second point was 2 over 1,000. I then constructed the kernel, which was a 1,000 by 1,000 matrix on these points, where the kernel between the ith point and the jth point, think of this as I over 1,000 and j over 1,000, was equal to the radial basis function, where I took the distance between these 2 points, squared it, and then calculated this function of it. And so I ended up with a covariance matrix that looks like this. So really this is a 1,000 by 1,000 matrix. It looks like a continuous image, but it's really a 1,000 by 1,000 matrix shown as an image, where points that are farther away, for example, this point here, so this point corresponds to the covariance between, let's say, this point here and, say, this point here. They're too far away according to my definition of B, so their covariance is essentially 0. So there's no correlation between these 2 points. However, if I get closer and closer, if I pick, say, 2 other points, for example, this point here and this point here, say these 2 points, then suddenly my covariance between those 2 points is large. It's closer to 1 because the distance squared is small compared to how I define B. So these 2 points, according to my Gaussian process, should be very correlated. Now, there's a lot of theory underlying kernels and Gaussian processes that we won't go through in this class. But what we can show is that with this kernel, as 2 points go closer and closer together, so as we have one point at, say, point 7, and then another point gets closer and closer to that point, we can see that this distance between those 2 points is going to 0, and so they're perfectly correlated. This function is going to 1. They're going to be perfectly correlated. What that leads to is that means that if I look at point 7 and I look at a point epsilon, infinitesimally far away from it, because they're perfectly correlated, their function of the random function f of x that I generate is going to be essentially the same at those 2 points. What that amounts to is that we have a continuous function. So that's the key thing. So what I'm showing here is actually a 1,000-dimensional vector generated from a Gaussian process, from a 1,000-dimensional multivariate Gaussian with 0 mean and covariance equal to this 1,000 by 1,000 matrix. And the perfect correlation that happens between 2 very close points, or the very high correlation between 2 close points, manifests itself in this vector by those 2 points being essentially the same value. The value of the function of the vector f at those 2 points are very close to each other. So we can really plot it like it's as if it were a continuous function. And it is. I could have partitioned this into 1,000,000 equally spaced points, and it would have been even more refined. But we get a random function. If I generated this one function and I got something that looked like this, if I generated another vector from exactly the same distribution, I might get something else. I might get something that looked like this. So this way I can generate random functions, and now I'm going to learn those functions based on the data that I have. So what that means is that my model hypothesis is that there's some function underlying the data. For example, this function was a randomly generated function that's now going to be underlying how the data is generated. But I don't get to observe this. What I get to observe is that randomly separated points. So here I pick 25 points in the space in which x lives. I then get a noisy observation of this function at those points. So for example, at this point, right around here, I missed it, I get a random observation of the function f where I have a mean equal to the function at that point plus some noise that is going to account for the fact that perhaps my measurements aren't exactly right. There's some noise in the system. So I get noisy samples of this function at different points in x. And so that's my data set. So my data set would be a pair here, xi, yi, where xi is the evaluation of this Gaussian process at the point x, And then yi is a noisy observation of that function evaluated at that point. What Gaussian processes are useful for is predicting new data using this framework. So we have a hypothesis for how the data is generated. We assume some underlying function, continuous valued function, and we get random samples of this function, and that's the data that we have. Now we want to infer this function so that we can predict the evaluation of it at a new point. X naught now is some new point. So the new point that we have is, for example, say here we get a new point, and we want to predict what is y evaluated at this new point, x naught. We want to learn a posterior of this function so that we can learn that at this point our function should be around here. So we'll predict a point that's in this region for the associated y with this input x. We can actually calculate this distribution on this prediction analytically. To see this, let's return to the finite dimensional space. So we aren't going to define the kernels yet. We're going to do it with no kernel definition. We're back to the X matrix to make it a bit more transparent. So we have this set up. Imagine we have n observation pairs, xi, yi, and we want to predict y naught given a new x naught. So according to our model, this observed data and this unobserved or partially observed data is all IID, or I'm sorry, not IID, it's all independent conditioned on the vector w. So we can write the joint distribution of y and of y naught and y using condition on w and then integrate out w. What that means is, let's imagine now that I have an augmented vector where I take the observed y and I have my unobserved y naught, now that I make the first dimension of that n+1 dimensional vector. Then according to my model, the distribution on this vector is zero mean. It's a multivariate Gaussian with zero mean, and covariance equal to sigma squared I, which accounts for the noise. So every single value in here has some IID component that's just white noise. Plus, now this additional matrix here, there should be a lambda -1, according to the original model. So remember, according to the original model, y was a zero mean Gaussian. So if I got rid of this y naught, y was a zero mean Gaussian with covariance equal to sigma squared I plus lambda inverse times xx transpose. That's on a previous slide. Now if I view an extended vector, an augmented vector, where I have one additional point here, y naught, and an additional covariate vector x naught, then we simply augment this covariance. The mean remains zero mean, and now the covariance becomes this extended matrix where I have along the lower right the original xx transpose, and now I have to add one row and one column to that matrix. So in my first entry here, I have the dot product between x naught and itself. Then in the lower right, I have the product x naught, and then I have that transpose. So what this matrix looks like is I have one point here, which corresponds to this point. I have one vector here, which corresponds to this. I have one vector here, which corresponds to this. And then I have the original matrix from my original problem. So now I've extended my covariance matrix to account for the one additional point that I want to model. A standard result now from Gaussians, which again I won't derive it, but what we can say is, what is the conditional distribution of y naught given the data and given x naught? So if you tell me the vector y and you tell me the matrix x and the vector x naught, but I know this part of the vector y, and now I want to predict this missing dimension of that vector conditioned on knowing all of the values in the remaining part of the vector. We can calculate this. It's a univariate Gaussian with mean mu naught and standard deviation sigma naught squared, where the mean mu naught is simply, so I'm going to get rid of this this lambda squared because otherwise my equations here aren't necessarily correct. We'll imagine that lambda squared is absorbed in here. Or, I'm sorry, lambda inverse. The distribution on this remaining dimension, conditioned on knowing y, the vector y, and knowing all of the vectors x naught through xn, is a univariate Gaussian with mean equal to mu naught, where mu naught is a function of the vector y and this matrix. Specifically, we take this row vector here, so that's this part, multiply it by the inverse of this matrix here, and then multiply that by y. So that's the mean. The variance of this is now equal to the original noise variance plus another function of this matrix here. We take this point here, and then we subtract from that the product of this vector times the inverse of this matrix times this vector, which is what this is saying. So we can take all of the entries in this matrix and this vector, perform functions of them to get a distribution on the missing value y naught. Okay, so the reason why I wanted to go through that example with finite dimensional Gaussians where we aren't thinking about kernels is that the Gaussian process is simply no different. We take all of the only difference is we take all of the dot products and replace them with kernels. So remember, we took all of these dot products in this matrix and replaced it with kernels. So we can replace this matrix with the kernel matrix constructed on the original data. We can take this scalar and replace it with the kernel function of these points. We can similarly replace these dot products with their kernel functions. So let's do that. So we'll define for a new point x. So I'm not saying x naught on this slide. I'm just saying for a new point x. This is a continuous valued thing. We can pick any point x that we want. Any point that comes into us, we evaluate it at that point. Or if we want to make predictions at an arbitrary point, we can pick an arbitrary point. We calculate the kernel function between an arbitrary point x with the entire data set that we have. So we're going to call this, we're going to give this notation the meaning that we take a point x and construct a row vector where we construct the kernel between that arbitrary point x and each data point. So the first dimension is the kernel between x and x1 and so on. So this is a 1 by n dimensional vector. And then we construct the kernel function between all of the data in our data set. So this is an n by n matrix where the ijth value of this matrix, kn, is the kernel between xi and the kernel function between xi and xj. So those are the definitions of those two things. Then if we want to predict what is the distribution on y, the corresponding y for arbitrary x. So now we have a function of the response y that takes, it's a function of the covariate x, given the data set, and given our evaluation at a point x. That's a multivariate Gaussian with a mean mu that's a function of x and a variance sigma that's a function of x, where mu is now calculated this way, where we take the kernel of the arbitrary new point to all of the data that we have, times the inverse of the kernel on the data that we have, times the observations that we have, y. That's the mean. And we have as a variance, again, the noise variance plus the kernel of the new point to itself minus this. So if we look at the previous slide, we're simply mapping points. Here we had a vector times an inverse matrix times y. In this slide, we also have a vector times the inverse of a matrix where we simply redefine these dot products to be the kernel functions. And similarly with the variance. Let's look at a toy example of what we would learn, the posterior of this. I took a Gaussian process. I randomly generated one. That's the black line. This is the ground truth function that I generated using the same procedure from the previous slide. I set the noise variance sigma squared to be extremely small, almost 0, so that the samples that we would get would be very close to this Gaussian process. I picked 9 points equally spaced out between the two extremes. So for example, the first point would be this as the input. So my first point would have this as the input and this as the response. So this point is x1 and y1, and I have that for 9 points. I then learned the posterior of y, this y, according to the previous slide. And remember, I can evaluate now that posterior at any point that I choose along this x-axis. So I evaluated my prediction I would make for any arbitrary point. I picked essentially 1,000 equally spaced points in this region to say what would I predict for the response if my input were, for example, this point here. The mean, as we saw from the previous slide, the prediction is a univariate Gaussian for each arbitrary point I pick. My distribution on the response is a univariate Gaussian with a mean and a covariance. That's a function of kernels between that arbitrary point and all of my 9 data points. So I'm showing here first the mean function as the blue line. So this blue line is mu of x from the previous slide. So this is the mean of my prediction, which you can see is shadowing the underlying Gaussian process. So this is what I think my mean, so I have a prediction of the underlying Gaussian process. Mu is the mean of that prediction. Then this red dotted line corresponds to sigma of x. This is my uncertainty. So what you can see is that as I predict closer to a point that I've observed, my uncertainty gets less. This essentially pinches the function. This point here pinches the function, my prediction, at that point, because I have data there. So I'm very confident about this point. But as I move away from a point, I get less and less confident about my prediction. So for example, in between these 2 points, my confidence in my prediction is much less. And so you can see that my variance increases, but then gradually as I move towards another point, it becomes more and more confident, and again I'm pinched at this point. So here the blue line is my prediction of the black line, and the red dotted line is my uncertainty of that prediction. And it gets more uncertain as I move away from points and more certain as I move towards points. Okay, so what we have here now is a way of making a prediction for any arbitrary data point that's a function. We're really learning an underlying function, and this function can take any arbitrary form. Notice that this is essentially, with this we're doing regression. We're not doing classification for this particular case. And so we're doing, in a sense, non-parametric regression. So we can learn any arbitrary function. If we wanted to do a linear classifier on this data, we would only be able to learn a line through the data. With the Gaussian process, what makes it so versatile and so popular and widely used is that we're learning essentially an arbitrary function that interpolates the data but then tries to smooth the data as well. So we're interpolating the data because here I've created a noise-free data set. I'm moving through each data point. If there was a lot of noise in my data set, I would be kind of doing a running smoothing function through the data set. And now we can learn arbitrary functions as defined by the data set to make our predictions.